Hi, my name's Chris. I'm from FlipMath, and I'm going to take you through today's lesson, which is on integration. And I've called this for area. It's a C2 module, part of the AS Maths course for SIA. It may be another module for yourself or another board, but this should be absolutely fine and applicable to any other board. The objectives. We're going to define the difference between a definite and indefinite integral, and we're going to use integration superpower to find the area under a curve. If you don't know how to integrate at all, you should go back to the previous lesson, which was just on integration. Everything you know backwards is what I called it, but C2.2.2.1 is the code that I downloaded to that fits in my schema work, etc. on that. Introduction is this. In the last lesson, we looked at how we integrate. You found out how to do it yourself, and then discovered the very big bad plus C. I stuck arch enemy in there in the notes because, you know, we're talking about a superpower in this. It's the Lex Luthor of the integration world, of the calculus world. Although I must tell you, of all the Superman movies, it's Superman 3 that's the scariest. I'm scared to all hell out of Superman 3 when Richard Pryor and everybody gets caught and the machine turns them into robots. It scared the hell out of me. And Lex Luthor wasn't in that at all. Anyway, just shows you how overrated Lex Luthor was as a body. The objective is this. We're going to define the difference between an indefinite integral and a definite integral. What you should know is how to integrate by rule. And we discussed indefinite integrals in the last lesson. When we integrate an expression such as 3x squared plus 3 with respect to x, remember that the integral sign and the respect of the variable that you're integrating with respect to makes the variable. You increase the power of the x term by 1 and divide by the new power. So x squared becomes x cubed, and we divide by the 3 as well. So it's 3x cubed over 3, and 3x squared, x cubed over 3 becomes x cubed. 3 just becomes a 3x, and don't forget your plus c, because there could be a constant in there at the end. If you're not sure where that comes from, like I say, go back to the previous lesson and hopefully it makes some sense. The presence in the plus c is one of the ways we can tell this is an indefinite integral. So even if you just seen the solution written down, you'd know that it was an indefinite integral. For the reasons that I explained in the last lesson, is that, you know, we don't know enough about the original expression to say whether there could have been a variable there or whether there wasn't. How do we make a definite integral, or how do we tell one? We'll start off by sketching the curve from above, right? The x cubed plus 3x, and in this case, I'm just going to leave that there. So this graph will continue to go up the left and right and has no easily defined start or end point. However, if we pick 2 points on a curve and integrate between those points, we get something different. So I'm going to blow this up a little bit. So I'm going to pick a point here and here, and I'm going to integrate just the bits between there and there, that part of the curve there. So this is the basis for a definite integral, is that I'm going to give it a specific start and end point that I can talk about. And this is the one thing difference between definite and indefinite integrals. You do not need to add a plus c at the end of a definite integral. And it's time to look at what makes integration such a useful skill. And one of the things that makes it part of any level 3 maths course, not just A level or otherwise. Okay, it's time for the superpower. So integration superpower is this. Differentiation seemed like such a much more deep subject compared to this. You know, it seemed like it had a never-ending supply of things that it could do and was good at. However, integrating gives the area between the curve and the x-axis, and we can use this to our advantage, some of which you might never get to use in your life, but when we come to study mechanics, you'll see it put in play. When studying pure maths, you get to know the theory of what you're going to do, and then generally in mechanics or applied maths, you'll show kind of uses for it. With this in mind, we want to find the area between 2 points. In mechanics, the area under a velocity time graph, for instance, gives you the distance that you've travelled, which can be very handy. So what are the calculate when we get the value of an integral at a point? So if we take the value of the integral there, so we integrate and substitute our x value in for 1. And we'll do the same with minus 1, and we'll subtract the 2. We'll get the area that's contained between these 2 points. So if I calculate the area for each point, and take one away from the other one, so I've got the upper limit, take away the lower limit, we get the area in between. So let's look at the notation for that. The difference between a definite integral and an indefinite integral is we still have our integral symbol, we still have our respect to the x, we have some function of x in the middle, but we have two limits b and a here. I'll show you those in a second, but they correspond to the start point and the end point of the bit of the curve that we want to find the area of. So the b is the value in the x-axis, the a is the value in the x-axis, and we're going to find out this area s by integrating. Okay. So our example is this: we're going to find the area bounded by the curve, the x-axis and the lines x equals 1 and x equals minus 1. And bounded is the word that we use to say the bit that's captured in between all those points. So between the y equals 3x cubed squared plus 3, the x-axis and the lines that we have there. This is the curve and the problem we've been looking at so far, so it should be familiar. First step, as before, is to integrate it. Then we have lines. When we have lines that close in the area, we call those limits, but it also changes how we write our integral slightly, just like was said. So, as an example, following on before, taking out the letters, our function of x, or our curve, is 3x squared plus 3 here. Our limits are between 1 and minus 1, so the upper limit or the biggest limit goes in the top, and the smallest one goes in the bottom. And we have our integral symbol and our respect to x. We had integrated that before, and we get x cubed plus 3x. When we do that, we normally write the 1 and the minus 1 outside. You'll notice that there's no plus c on this because it's a definite integral with limits and we know a bit about it already. So for x equal to 1, I'm going to substitute x equal to 1 into our x cubed plus 3x. I got 1 cubed plus 3 times 1, that gives me 4. And for x equal to minus 1, I get minus 1 cubed plus 3 times minus 1, which equals minus 4. Remember that the area is what you get when you subtract your upper limit, take away your lower limit. So it's the difference between these values, so it's plus 4, take away minus 4. You'll notice that the minus becomes a plus, and you have plus 4 gives us plus 8, and we usually write, if you want some units, square units at the end. And that is the answer to the area bounded by the curve y equals 3x squared plus 3, the x-axis, and the lines x equal to 1, x equal to minus 1. So let's look at another example. Example 2 is from January 2012, say a past paper. And it says the curve y equals x minus, or 8 minus x to the power of 3 over 2 is shown below. And I'm going to bring it in from the side. There you go. Find the area bounded by the curve and the axis in the question. So they want the area that's bound by the curve, which is this bit here, and the two axes. So the x-axis and the y-axis. So the x-axis is kind of simple enough because that's what you do when you integrate. You get the area bounded by the curve and the x-axis. In this example, the question wants you to read the values from the graph for the limits. So the upper limit and the lower limit. So we're going to identify the limits, so the highest point and the lowest point of the graph it wants to measure from. And from our graph we can see that they're x equal to 4 and x equal to 0. We're going to set up the integral then, or the definite integral. So it's the integral between 4 and 0 of 8 minus x to the power of 3 over 2 with respect to x. If I integrate, I'm going to get 8x, so the 8 gets an x put in front, 3 over 2 and 1 gives us 5 over 2. Dividing by 5 over 2 or dividing by a fraction is the same as multiplying by a fraction when you turn it upside down. And that becomes 2 over 5. And if you want to do 1 divided by 5 over 2 on your calculator, you'll see that it gives you 2 over 5 as well, between 4 and 0. So our 4 and our 0 would normally be written up here like this, but I've written between 4 and 0 there. Okay. So we're going to substitute in our x equal to 4 and our x equal to 0 into this. So we're going to substitute our limits in. When x equals to 4, type it into your calculator, 8 times 4 plus 2 over 5 times 4 to the power 5 over 2, we get 19.2. When we put in x equal to naught, 8 times nothing plus 2 over 5 times nothing gives us nothing. And the area is the difference between, so it's 19 minus 2.2 minus nothing, which is 19.2 square units. Easy peasy. So I've given you one where they've just given you a curve and the limits. This one, they've drawn the curve for you, give you the equation, and asked you to identify the limits. And we'll have one more bit to go. So the diagram below shows the curve modeled by the equation y equals x cubed minus x squared minus 4x plus 4, like so. And this is using I've modeled this curve using a program, and it's given me an area here, and it's not correct, and I'll show you why. This is all a little different. Okay, so computers are all well and good, but many of them, and even many of the times you'll go on and look for like calculators online that'll be able to calculate the areas on curves, will have problems with this kind of problem. So why is this a little bit different? Well, it has two regions. It has a curve that's above the x-axis like this, and it has a bit that goes below it here. And we'll have to do these slightly differently. Okay. So I'm going to examine what happens when we find the area of the smaller portion that's under the x-axis. So I've just taken a bit of it here, and I'm going to highlight this bit here. So you'll see that the limits are 2 and 1 between it, and I'm going to integrate this expression and do between the limits of 2 and 1. So x cubed minus x squared minus 4x plus 4. When I integrate, I get x to the 4 over 4 minus x cubed over 3 minus 2x squared plus 4x between 2 and 1. And I'm going to substitute those values in. There's the values, substitute in what we get. And ultimately, we get minus 7 over 12. This is negative value. Okay, and you can check, I put through each of those steps there. You can check them when you put into your calculator what you get. Let's look at negative area. You'll see that this every time you calculate an area just like this, so kind of dips under the x-axis. So in some problems that include regions below the x-axis, the resultant area will show as a negative. Area can't be negative, aside from like a theoretical black hole or something. So what we've got to do is negate the area and add it to the other one. So we're going to negate the area. So kind of, if you want to think about negating the area, we're going to forget about the negative sign and add it to the other one. So our area for the last calculation is therefore not minus 7 over 12, but it's minus 7 over 12, which is plus 7 over 12. So the area of this bit, if this bit had been up above the x-axis up here, would have been 7 out of 12 square units. But it wasn't, it was below the x-axis. And because of that, it got a minus sign. But area can't be negative, so we negate that area. When problems have positive and negative areas, you've got to work out these sections separately. So, using the limits. So I do between 2 and 1 as my first limit problem. And then in the next part, we're going to do between 1 and minus 2. And do our limits so separately. If we do the two of them together, what it'll do is it'll work out the area of this and take away this bit down here, because it reckons the area that's a negative, but that's not. Because what I'm saying is that actually can't have a negative area. That's where they have got the minus 10.67, etc. for our area there. But that's the rule. So when problems have positive and negative areas, work out the sections separately and add to get the total area. So if I go back and we're going to look at the area of the other section, so the big section between 1 and minus 2, we're going to take our integrated expression, which is that, and we're going to do between 1 and minus 2. We've already put when 1 is in, we got that. When I put minus 2 in, the expression, I get that. When I solve all that down, I get 45 over 4, or 11.25. The total area is then 45 over 4 plus the 7 over 12 from the wee small section over here. We add those together, we get 71 over 6 as a fraction, or 11.833333 square units. And that is our third example. So one with positive and negative area. Next time on C2.2.3, which is the last part of integration, what can we do to calculate the area when we can't integrate? So if we get an expression or a graph or something that we don't know the original curve for, how can we calculate that area? We're going to look at a thing called the trapezium rule. And it's going to come to the rescue. Sticking with the superhero theme, it's going to come to the rescue. Dum, 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 dum. Our objectives were to define the difference between definite and indefinite integrals and use integration superpower to find the area under a curve. Hopefully we've done both. Practice, practice, practice. For exercises, solutions, quizzes and downloads around the subject, go to flipmath.co.uk and search for integration. Along the top of the front page now, there's a little search box and you can type in integration there and search from there. Feedback on others should be sent to @flipmath, or any glaring errors or mistakes, stick in the comments down below as well. Thank you for watching, and I'll catch you next time.